Well, thank you for that kind introduction. It's great to be here. We were talking just briefly, Jim Soha and I, briefly about automotive at the Design Automation Conference and so on, and it's really surprising because electronics have been, in my career at Ford, and now it's 35 years, have been a growing part of the automobile, and in fact are really taking over many of the systems in the automobile today, and as you'll see in our presentation. So really it's a good fit in what you focus on here in terms of tools, processes, data management, and so on is critical for our success into the future. And so Jim and I are going to take you through, I'll kind of present and share really from an automotive perspective where we're applying the technology, how we're applying the technology, maybe giving you a little bit of a taste of how these systems are integrating together, creating the new systems in the future, and creating challenges for us. And also making sure that focus on why automotive is a little bit different. Certainly we'd like to be the same, and everybody wants to think they're different and special, but we have some very significant challenges, and it's important for us to talk about. Jim will focus a bit deeper on how the tools can effectively be used for the challenges that we face. Jim, any comments on agenda?
Well, I guess first of all, I will try to squelch the rumor now. I'm not moving to Samsung. Just to pick up on that slide. And my perspective is going to be very much from the tools and process standpoint, not only MathWorks tools, but also the tools and integration of tools from various vendors that we work with, and looking also at development processes as they occur in automotive, because I work a lot with the key customers in automotive, but also across industries, because there are some common elements that are important, but there's some key differences as well.
Very good. Thanks very much. And this is a unique kind of presentation format, dual keynote speakers, not dueling keynote speakers. So hopefully we'll present it in a way that makes a lot of sense to you and integrates together very well. Again, our background, as you can see, a lot of experience both Jim and I have, certainly on an automotive perspective. Let's just really get started. And for us at Ford, it really starts at our founder. And we'd like to talk about this ad that was in the newspaper in 1925. And the reason I bring this up first is because all of us here are technologists, right? We love technology. We think about it every day. In fact, some probably think of it 24/7. But what's really important to customers is experiences. Experiences are why people buy products. Experiences are how people's lives are changed and why people fall in love with the products they have too. And so when we think about experiences, we think about experiences as simple, intuitive, seamless, safe, and secure. These are fundamental tenets that drive creating products that people will use and love and be passionate about. Certainly, we want those products from an automotive perspective these days to focus on personalized, knows me well. The product understands it makes my life better because it anticipates my needs before I'm even asked. And you can imagine thinking again how that can be created with data and access to information, connectivity, and so on. It attracts and creates loyal customers. Again, we found with products like Sync, integrating into people's digital lives, people find they can't live without it. It's a reason to buy. Sync has been really a success story for us in that integration with the device that you bring into the vehicle has become so important. Not only regulatory, where you can't text while you're driving, but also because it helps bring information that you use into the vehicle and allows you to use that time in the vehicle, which is time being so precious, more productive. So really, you'll see a constant theme from my messaging around it's not just the technology. Technology is an enabler for creating great experiences, and experiences is what it's all about for us in the auto industry. Now, how do we define experience? Certainly, the senses, the touch, feel, and the see. What you touch in the vehicle, how you, the seat position and so on, how you feel, that exhilaration. Certainly, a lot of people are really excited about the Mustang that's coming soon, and we've had a real successful order debut in Europe and sold out. But also it goes beyond just what you have, what the standard senses are, but it's the entire experience, from before purchasing it, through the purchase experience, through the ownership experience, and afterwards. And I think you're going to see increasingly what's important to us is the experience through the entire life cycle. Today's consumers with consumer electronics are experiencing downloads, updates, new features. Just down the block here, there's a company that you know pretty well that talked about their latest operating system and new features and new excitement that they're going to be able to download in the future for customers. That's an expectation now that people are bringing into the automobile as well, too. It's physical and digital interactions as well. So the digital world is invading, and being able to process that information in a way that creates these great experiences is critical to us. It has to work seamlessly, working together as partners, no boundaries, basically meaning that how the vehicle interacts with the driver, interacts with the driver's ecosystem, just needs to work. It's really got to be seamless. None of this complex just because you're using a particular device or whatever, some complex things that you have to go through. And so we got to keep the driver focused on their primary function, and that's driving. And all of these great experiences are going to allow us to differentiate going forward in the future, and they all have to just work. So if you look at where we've been and where we're going, in the past, we had purely mechanical systems and electromechanical systems that drove the vehicle, drove the powertrain as an example. Today, electronic systems. In fact, I joke sometimes that there's an electronic system in just about every subsystem in the vehicle, from antennas in the glass to sensors for tire pressure monitoring in the tires. You name it, electronics is everywhere. We're also, from a design point of view, moving from 100% focused on getting the vehicle perfect at launch, perfect design, perfect capability, perfect quality, to one that says, yes, we still have to have that perfect at launch, but we also have to leverage software to continuously improve the product, continuously provide surprise and delight over the entire ownership experience. And software is a key thing we can leverage to do that.
So when you look at the things that work, what's today's state of the situation? Well, Jim, a couple of slides ago, showed this picture. It's a picture showing you some of the driver assist features in the 2013 Fusion. Rear camera, lane keeping, some of the new functionality that people will consider interesting and valuable as they make their car buying decision. But in a car, there are probably 50, 75, even 100 ECUs in the vehicle. And an ECU is not an engine control unit. It's not really focused on the engine. These are general electronic control units that manage and deal with all the different areas of functionality in the automotive domain. And so when you look at the functionality that are being handled by these ECUs, they comprise lots of behavior. Engine management, transmission management, so that you have a smooth shift in your automatic transmission. Stability systems for your chassis, so as you go around a curve too quickly or do a J-turn, you don't flip over. Traction control, for those of us in New England, pretty valuable. Various types of safety systems, airbags, and so on. All of these things are driven by electronics with the associated software. Now, these are features, functionalities in the automobile that are not simple. They're very complex, each in its own right. Let's take, for example, adaptive cruise control. This is functionality that relies on a forward-looking sensor, anticipates when another vehicle is either slowing down in front of you or is moving into your lane, and does the right thing, applies the brakes, helps you to move, steer, etc. When you dig into the functionality within adaptive cruise control, it actually comprises the coordination of several different things. It includes functionality engine management system because it needs to throttle back in a smooth manner. It needs to interact with the electronic stability program in case you need to do an evasive maneuver. And it also has to deal with the braking system. So even though we call it adaptive cruise control, it's the confluence of several different significant systems in the automobile. Another aspect of the things that still work is the successes that have been enjoyed to date by the automakers and their tier 1 suppliers. I brought together a series of examples that demonstrate the successes. Some of them are more interesting, in my view, than others. Perhaps some of the battery management for hybrid city bus in China, or engine management systems that work with compressed natural gas and propane systems, and so on. But you'll see the variety. Suspension systems, engine anti-knock devices, lighting control that coordinate with doors being open or not open, reversing wipers. These are successes not because they created a big splash when they were introduced, but it's because we have been able to forget the fact that they are there, because they just work. We can ignore them and rely on them all at the same time. Some of these features that just work, unbeknownst to us, is They're important for you guys. They may have fewer lines of code in the embedded systems, perhaps than HMI or an infotainment system and so on. But they are responsible for many of the essential features and functions in the vehicle. And they're necessary to be developed well and verified correctly, because in order to meet the regulatory needs and also the consumer interests. And there's a lot of silicon in this area of just work functionality. So when you look at the trend in automotive and look what's new, what's coming on, what's going to consume the next set of chips and software? Well, certainly one of the big trends is sustainability. The desire to create more green vehicles, to be better to the environment in every manner and fashion. That includes things that are driving the electric vehicles, the hybrid electric, the fuel cell, and other technologies that are taking place. It means new types of components. When you're dealing with hybrid or you're dealing with fuel cell, you're bringing new subsystems into the vehicle that didn't exist in the traditional internal combustion engine-driven vehicle. These include electric motors, battery management systems that must be very, very good and smart, gearing systems that will deal with the multiple propulsion systems that are going to be under the hood, regenerative braking and how that's going to interact with the battery and the battery management and the electric motor, algorithms that have to mediate and manage the interaction between these different types of new components that are being introduced. And it also means, from an electronic standpoint, an increasing reliance on power electronics and smart power management. New sensors are being introduced in automobiles as well. LiDAR, radar, ultrasonics, cameras, all around the vehicle and in the vehicle, looking forward, looking to the side, looking inside as well. That requires also electronics and algorithms that can process that data to make it usable for decision making. And then popping to a higher level, there are the features and functionality. Safety features that are active safety and passive safety features, such as the one I've mentioned. Automated behaviors, such as the things that Jim will talk about later in this presentation. Other things like prognostics and predictive maintenance, understanding the current state of the pieces and components of the automobile so that it knows, and the service center knows, and you know when you need to bring it in for a maintenance check. That requires data, it requires algorithms to be able to make the decisions wherever the decisions are being made.
So you look at all the complexity and you say, well, or some of you may be saying, well, so what? We deal with 14 nanometer transistors, billions of transistors, a lot of complexity and so on. So what's so hard, what's so different about the auto industry? Well, first of all, we can't design cars like we design cell phones. Our timing is a lot different. Cars can have 16,000 to 18,000 to 20,000 parts that have to come together in a cohesive way, working together to create the functions that we talk about. We don't have the latest processors and technologies. We're designing, as I'll point out in a few minutes, quite a bit ahead. You introduce processors in the SoC business, you know, at a cadence that we can't keep up with, that it's difficult to keep up with. And so the gears on the bottom say, you know, kind of point out that we've got to find ways to match what we do in our automotive cycle with what goes on in the consumer electronics. You know, and customers ask, and I have a slide full of questions that customers ask about why can't my vehicle be more like my cell phone or my other electronics? And why does it take so long to integrate these new capabilities? You know, a new operating system that comes out, why can't it be in the vehicle, you know, by the end of the year, as an example? So some examples of challenges. Our design cycle, 24 to 48 months to develop a brand new vehicle from ground up. All right, 48 months would be more like a brand new platform, new chassis, new suspension system, new body interior, having to go through crash and so on. We also have to design for a design life of 10 years. So when we make those big investments in a brand new platform, we don't expect to cycle through and replace that platform for up to 10 years. And in addition, customer expectation is that they can be driving for 7 to 10. In fact, good news for us lately, it's gone down. During the financial crisis, the time in service for vehicles, the fleet was approaching 10 to 11 years. And so it's nice that customers are refreshing a little bit more often, getting more to the norm in the past, which has been about 7 years. We start our development 2 or more years before we start production. So we're making commitments on SoCs and silicon and software and so on 2 years before the vehicle goes into production. In many cases, for cell phones and consumer electronics, you've probably gone through 2 cycles of designs in that period of time as we're getting ready to introduce a product. And then electronics have major upgrades required every 3 years. You know, adding new performance and new capabilities means we can't go at this 10-year cycle of the vehicle. So matching these 2 cycles is really important. And of course, the complexity of systems and components and the testing and certification and regulatory requirements is very critical to us. Compressed time to market and still meeting the quality requirements is really important to us and an important challenge. You know, the most important thing for consumers of cars and trucks is to getting from point A to point B. You can never get in the way. We can never get in the way with that. They depend on their vehicles for transportation to get them to their jobs, get them home safely, take them on trips and so on. And all this functionality, all these great experiences that we can create that are possible to make a better experience in the vehicle can never get in the way of that fundamental point. Software also does enable flexibility, but as you know, software is a bit different beast. It's not like designing casting or a stamping or some other mechanical part, or even, in effect, a piece of silicon or whatever. Software has a unique design process, and in fact, it's hard. You can ask anyone about creating bug-free software, and they're going to give you that stare, well, I can't guarantee it's bug-free. Consumers are expecting their cars to respond to change like consumer devices. The frequency of upgrade and change with electronics, in fact, the incentives that you get for upgrading your phone, my daughters remind me of that all the time, really drive a different view of how the automobile should be, right? It's a purchase that you make, you know, the second probably most expensive purchase most people make. And so they expect to have the opportunity now, given the drive in consumer electronics, to be able to upgrade and keep their car fresh over time. And of course, there's an expectation now of always being connected in our digital lifestyle with smartphones, tablets, all these electronic devices. We are connected. We have access to important information that can help us make better decisions all the time. And now the expectation is in vehicles as well to do the same. In addition, cars and trucks have to be affordable. In the end, it is a major purchase. It is a purchase that people focus on price. In fact, many Americans focus on what their payment is going to be to determine what features they'll get on a vehicle. And so how do we add more and more and more safety, security, all these great experiences and features, yet make it affordable for customers? We refer to it as democratization of technology, and it really requires leveraging scale, which isn't the same as the CE scale. In the consumer electronics business, you know, Apple or Samsung may sell 4 million phones over a weekend, where we sell 4 million vehicles in a year in the US. So different kind of scale requirements, but we still have to leverage as much as possible to democratize and keep our vehicles affordable. Must design for 16-year-olds as well as 60-year-olds. The expectations of young people today are different than 60-year-olds who grew up with records and without microwave ovens. Today's young people have a different feel for transportation. Many of them don't even own cars, or that isn't their first thought. We had I had a discussion a couple weeks ago, and it is now become a very lifestyle-oriented need. So young people out of college may say they don't need a car. By the time they get a family and a house and children, the story is different, and having transportation, having that flexibility is important. But it is going to change over time with urbanization. We'll talk a little bit about that. Finally, our margins are pretty slim. You know, we're not an industry like the consumer electronics business where we have a lot of profitability per unit. We have very, very slim margins and very, very competitive. So cost is extremely important to us. Finally, our regulatory requirements. They're not always understood by our consumers. In fact, many of you might argue, why did you guys have to do this? Why don't you let me enter destinations into my navigation system while driving? Right? All of these are regulatory requirements or regulatory guidelines that are put in place for safety purposes. And again, not always understood by customers, but again, required. Of course, safety is not just about crashworthiness of the vehicle and keeping drivers and passengers safe. It also includes today things like driver distraction. What might take a driver's attention away from the road? How do we keep drivers really focused and performing at the top level as they operate a vehicle? And then finally, emissions and fuel economy. And I'd suggest that kind of emissions and fuel economy were really at the start of driving electronics into automotive. When I began my career 35 years ago, powertrain controls was just at the beginning and really starting to be leveraged to meet the stringent regulatory requirements, and it will continue as more electric vehicles and other forms of fuel economy savings features come into play. Now, this chart I put together really to give you kind of a comparison. We think about our auto industry, and we think a lot of it about the requirements as similar to the consumer business, because it is a consumer product, but also with the regulatory and the expectations of the aircraft industry. So if you look at some of these items like expectations that it just work, you expect airplanes to just work, right? There's no no room for error in an aircraft in a flight. On the other hand, your smartphone, if it resets occasionally, as long as it doesn't do it too often, or if you have to load in new software and it takes 15 minutes to download and update and so on, you kind of put up with it. It's not the case in the automobile industry. And in fact, if you look down a number of these things, whether it's cost or operating environment, you see we take from both sides. We're driven by the consumer side of the business as well as the aircraft and aerospace industry. And I've highlighted a few of these. You can see expectations on just working more like an airplane, production volume and cost more like a consumer electronics business. You can see the product lifetime, regulatory requirements, and so on. So we've got a little bit of both that we have to deal with in making it kind of a unique proposition. Now, still, consumers frequently ask these kinds of questions. Again, as I pointed out earlier, why can't it be more like my cell phone? Why can't I just use my iPad to control the radio and so on? I purchased a phone based on not only what it can do now, but what it can do in the future. Why can't my car be more upgradable? Why can't I get my car and just keep doing what I was doing outside, get in my car and keep doing what I was doing on the outside? Again, all of these things are new requirements or new questions consumers ask, yet they still want to be able to have the fundamentals of helping me use less fuel, need to get there in time, efficiently, keeping me safe, and keeping my car working. So again, a whole new set of requirements on experiences on top of the ones that were always there. Now at Ford, when we look at experiences, we tend to bin them in these four categories. This helps us kind of focus on our overall strategy: quality, green, safe, and smart. Really, quality is really the price of entry, and green, safe, and smart are the experiences that will really garner differentiation with their competition. And I'm going to take you through a few of these. How do we make the experience simpler and safer? On the safe side, driver assistance features and safety features, sensors, radar, ultrasonic cameras. You see examples. Jim pointed out some examples of adaptive cruise control, blind spot detection. You can see lane departure warning and so on, are all the kinds of features that help keep us safer by giving more information to the driver, assisting the driver in their driving experience. On the green front, software connectivity helping with a greener experience. You can see a myriad of different kinds of applications of electronics and software, especially in the area of electric vehicles and so on, but also in basic vehicles, new transmissions, controlling EcoBoost or turbocharged engines, all continuing to help driver get better fuel economy for existing vehicles, whether they're gas or electric or hybrid. In the area of smarter systems is a big category. In fact, the category we think that provides the most differentiation, providing safety, providing green or fuel economy and so on, are fundamental entry-level requirements. Smart areas are the ways we can differentiate our vehicles, making customers or creating experiences for customers that they feel are unique and different. You can see some examples here, and I have a short little video to show you something called fully assisted parking aid. In this example, and we'll talk a little bit more about automated and autonomous. Here's an example of a vehicle. It's combination of an animation and some live action. But think about the experience of a tight parking space. And for me in Michigan, Jim, probably in the Boston area, in the winter, the cars aren't nearly that clean. And having get in a tight space, rubbing against the cars, possibly denting the car, scratching the paint. And imagine an experience, and we've actually built these with our supplier partners, where the vehicle finds the parking space for you. We do have that in production today, but allows you to actually get out of the vehicle and operate the vehicle and park the vehicle remotely from outside the vehicle. Again, with a handheld device that has a dead man switch on it to make sure that the driver is still in control, but again, allowing you to fit into that tight parking space without having to squeeze in between cars. Think about the confluence and interaction between different systems, ultrasonic systems, radar systems, camera systems, and so on, plus the connectivity between the car and the device that the driver is using to control it. All are important parts of the application of the technologies that you guys are creating and that we're working on with companies like MathWorks and so on to deliver seamless experiences. With all of that, there are two areas that I want to focus on a little bit more, or two themes for today. One really garners a lot of attention. First of all, assisted and automated autonomous driving or autonomous driving. Again, nearly everyone is working in this area, some auto companies and some non-auto companies, and it's a big area of opportunity. It's all about robotics and so on, and quite a big challenge. The other area is really about fully connected mobility, and why this is such an important area is because as we see the growth of automobiles around the world, we see the growth in urban areas that really can't support the amount of traffic and the amount of volume of vehicles. And so how do we create an experience that is a seamless experience that connects different forms of mobility, whether it's walking, riding a bicycle, getting on the bus, and then eventually getting in your car and making it a seamless experience as you go from point A to point B. So future of mobility is an important project that we're working on here at Ford. On the driver-centric to assisted to autonomous, what's really key here is fusion of sensor technology. Right? There isn't one sensor that does it all. I have a short video that I'll play that will run over the top of this in a second with showing LiDAR. But just remember that radar is very good for range sensing, right? So distance to an object. But it's not very good at recognizing what type of object is it. Is it a pedestrian? Is it a tree? Is it a bridge? Is it a guardrail? It's just good for range. Cameras are great for identifying and classifying an object. Is it a human being, a pedestrian, a dog, whatever? But they're not good for range sensing. It's much more difficult to get accurate range sensing. So the combination of radar and camera, you can see fused together, forms a much more robust system for these kinds of experiences. So as we see moving forward from where we are today to ultimately automated or autonomous vehicles, it's really that progression of bringing and integrating these systems together seamlessly. The ultrasonics, the cameras, the collision. So taking something like forward collision warning, right, and with brake support that allows you to see vehicles, the radar system to see vehicles and keep a distance in front of you. Combine that with lane departure warning and lane keeping to keep you in the lane. Now forms a new feature called traffic jam assist. Traffic jam assist at less than 25 miles an hour will keep you in the lane in those jam-packed 101 traffic jams without you having to control the throttle or the steering or whatever. Semi kind of autonomous, but you can see as we progress toward automated, we'll introduce those systems first and then keep building on those systems till we ultimately get to an automated vehicle. So example, just to show this split screen here. So those of you that haven't experienced LiDAR systems, again, great capability to detect objects around the vehicle. Hopefully it is very viewable. You can see on the left-hand side the actual, what the driver sees and what the LiDAR system sees. So again, very accurate ranging of information, but not necessarily the best on classification. But again, a newer kind of sensing system that will be fused with other sensors in the vehicle to create autonomous and automated driving. Now shifting to the other theme on connected vehicles, we hear a lot about, all of us hear a lot about the Internet of Things and Internet of Everything and machine to machine and so on. Cars are going to become just another machine on the network, on the Internet, right? They're going to be connected all the time, and they need to be connected optimally, right? Whether it's a cellular connection, a Wi-Fi connection, or other, they're going to need to transition between those seamlessly. Much today, like a cell phone, as it moves from tower to tower, and the customer never detects it, the vehicle, as it moves about, is going to need to maintain that connectivity. And it's also going to have to connect across various ecosystems, all right? Ecosystems where my information is stored versus where your information is stored. If I'm in the Apple ecosystem, it's got to work with Apple. If you like Google, it's got to work with Google. If you like Microsoft, it's got to work with Microsoft. So being able to be agnostic and support whatever ecosystem is really key in the connected environment. And again, a lot of work needs to be done in that area on standards and so on to help us get there. So also, connectivity can't be guaranteed. And so transitioning between onboard and offboard, we like to use the example of voice recognition. Today's voice recognition systems are typically onboard the vehicle because we can't depend on that connectivity. You can't go out to the cloud to change the radio station FM radio station on your vehicle. You want to do that locally, so continuing to use some level of voice recognition in the vehicle, but then for more complex tasks, search and so on, you might want to go out to the cloud. How do you create a seamless system that the customer can't detect whether it's being done locally or out in the cloud? And again, a challenge for us going forward. The human machine, and the voice recognition kind of brings up this idea of the challenge of the human machine interface. Bringing all these experiences and new connectivity and new data, new information into the vehicle has to come with a way for a human to interface with the machine. And it's not, it's not just normal kinds of interfaces you'd see on a phone or whatever. You got to be able to do it at 70 miles an hour, right, without distracting the driver. Consumer electronics is still experimenting. It seems that the new operating system just introduced this week again makes changes to that human-machine interface. In the consumer electronics business, still searching for the ideal kind of interface. And again, if the consumer electronics business is struggling, you know that we're not far behind and have our own challenges because we have the distraction issues to deal with. And again, some may say, well, this isn't going to be a problem because when we get to autonomous vehicles, you won't have to worry about any kind of controls. The driver just gets in and goes. Well, what if a system breaks down? How do you change the move from an autonomous mode to a driver-controlled mode seamlessly and quickly if the driver hasn't been paying attention? So we have a lot of challenges in these areas as well, too. So what will it take to deliver these two themes? Certainly algorithms to fuse sensors. I mentioned that a couple times, probably overemphasized it, but it's really important. Methodologies that assure high quality and safety, like ISO 262, and the processes that support us delivering on it. Specifications. It isn't a business anymore where we define our own specifications. We've got to work with you guys and others, things like Wi-Fi and Bluetooth and so on that are consumer electronics. How do we leverage those and not create new ones? TCP/IP, Ethernet ABB, and so on in the vehicle. How do we leverage those instead of starting from scratch? How do we use as much that already exists out there and build upon it as opposed to starting new every time and creating new standards? Privacy and hacking is a big issue, and we it seems like every day, whether it's eBay or whether it's Target or whatever, we hear about that. How do we create trusted systems that really, again, people can trust with their personal information, so we can create that personal experience, as well as safe systems so people can feel comfortable in their vehicles that they are protected and all the safety systems are intact. Feature integration in Moore's Law, more for less. We get the best savings. Being able to keep those price points in vehicles, being able to keep vehicles affordable, really requires leveraging what you guys do really well, and that's integration, more function, more capability, more performance, so allowing us to integrate more features at great cost. And then seamless integration to the cloud and cloud services is important, as I mentioned with the voice recognition example. It also means unprecedented cooperation between our industry and other industries like yours. So really key to going forward. So software, silicon tools, and processes will continue to contribute to solutions the auto industry needs. Now, creating the experience where will automakers focus? You can see Experience design, experience design. You know, you can count the number of times I talk about experience versus technology in this discussion. You see the car is part of a bigger system. It needs to be connected at all times. Can't compromise quality or safety. You know, we're going to use software. We need software. Upgradability is really important, and attention to customer needs can never be compromised. So it's the synthesis and model-based systems and approaches with data is really key to moving forward. Some examples for the future: more sharing, communicating and testing with models, more use of APIs and standard interfaces, more standard information in physical architectures. The vehicle is becoming its own data architecture, having to have its own data architecture so we can share information on and off the vehicle between different systems. And we need smarter test and verification and validation. So really, auto manufacturers are now focusing more from silicon all the way through to final application, needing the support of tools and processes to help develop those efficient systems.
So listening to Jim's comments about experience, something that struck me, which is how automotive differs from a lot of other industries. And it really isn't explicit in how we've talked about this so far. When we talk about experience, it's really focusing on the centrality of the person, okay, the primacy of the person. And there are probably several reasons for that. One of them is that they are an integral part of the system, okay? They are the driver, they are the motivator, they are the person whose wish has to be met by the vehicle. The automobile is an immersive environment. We talk about immersive environments, you actually get into the car. And so it's not only about the electronics and the heads-up display and all that kind of stuff, but it's about the material, the look and feel of the fabric, okay, the line of sight out of the vehicle. All of those are key aspects that are part of the automotive heritage. And so those are important, and especially an interesting puzzle as we move toward more automated, autonomous behavior. A key aspect also of automotive is the emotive aspect of it. How does the car feel as you push the gas pedal or tell it to go forward with whatever means you have? How does it feel as you go around the curve? How are you going to create that emotive appeal that differentiates your vehicle from someone else's? That's a key aspect of automotive I think is really unlike any other industry that I'm associated with. Jim, in his last slide, talked about one of the key aspects of the new going forward approach in terms of design and development processes, which is sharing, communicating, and testing with models. And when we think about that, we think of that as model-based design. Now, what does that mean for us? It means, first of all, starting very early in the process, conceptualization of the requirements, trying to understand how the electronics, the software, the materials, the road, the driver all need to interact in order to make sure that you are able to meet the requirements, make sure they're feasible, okay, and addressable, but also make sure that you're able to do design exploration and optimization across the various domains and across the various systems and environments that the vehicle has to operate in. So let's take the example of minimizing fuel consumption for a vehicle design while meeting the performance objectives. One key aspect of that is figuring out in an automatic transmission, when do you shift from gear to gear to gear as you're accelerating, decelerating, going uphill, going down a hill, merging into traffic, and so on. So some of the key aspects of this are the transmission, the vehicle, and the control algorithms. When we think about system-level modeling, we think about creating a high-level system that's able to represent and simulate all those different attributes of the system, all the key aspects that will drive the question of fuel consumption and performance. And you need that entire model, even if at the end of the day you're going to drill down and only focus on one particular node of it, which is the cost function. How is it actually going to behave based on different shifting strategies? What's the fuel consumption going to be? When you take the set of system models and couple them with the requirements or the test cases, however you want to think of it, in automotive, one of the key aspects is driving cycles. Some of the mandated, defined cycles, urban, highway, and so on, for how the vehicle needs to accelerate, decelerate, go around different terrains, go uphill, downhill, and so on. And that's the way that the EPA mileage ratings are set. So when you bring those together, you're then able, from a model standpoint, to take the characteristics of the driving cycle, take the characteristics of the vehicle, and do optimization to really let the machine, let the computer do the design optimization for you. So what we're showing here is a little video where it's going to march through and go through a series of steps. You'll see the lines which represent the changing of gear shifts in terms of the different strategies. And it's optimizing based on a certain set of cost functions. Each time it's showing a different line, it's actually running the entire drive cycle. Okay, so it has to be a fast, high-level simulation that gives the engineer the insight that they need. And the insight is this: a detailed description that given different shifting strategies of the transmission, what would be the fuel consumption? What would be the performance? What are the trade-offs that are possible given the different design approaches? That then lets the engineer decide, based on the certain scenario, based on the certain requirements, based on the different marketing of the vehicle, where they should go. A second aspect of model-based design is the ability to automatically generate code, to try and minimize the bugs that are created, that are typically introduced by human error and manual programming, to enable optimizations to be done automatically as opposed to manually. I'm just re-showing some of the same user stories that I mentioned earlier, because these are also examples of situations where the automotive systems that are shown here use automatically generated code in their systems. And it's worth pointing out that these are not simply the large, complex behaviors like engine management systems, but also very small team behaviors and small functionality behaviors, such as reversing wiper motor systems. Another key aspect which is very critical in automotive, perhaps second only to aerospace, is the verification of validation. There's a host of technologies that are available and needed when you talk about using models in the development process. Some of the techniques are model-based. They perhaps require analysis, simulation, or formal methods, approaches on the model representation. Some of them are code-based, because at the end of the day, what is going to be certified is the code running in the vehicle. So there are a variety of code-based techniques that are needed as well. And there are some techniques that need to span the model and the code, because you need to have some continuity of the development process as you think about and conceptualize your design in the model, as you think about how it's going to work in the integrated system in the automobile. When you couple these things together into a process, and this is just simply a characteristic description of a process, you can think of the technical requirements. And the technical requirements in automotive are vast, spanning, created by different groups, and in many cases are in conflict with each other. And so it's necessary to use techniques like modeling to refine the requirements, to make sure that the requirements themselves are valid and feasible. They lead naturally to a set of executable specifications. What do the designs need to do, both at the system level and at the various subsystems level? The modeling process really is a core aspect of the design process. You iterate to understand different approaches and different trade-offs and different choices. You refine the ideas to add more implementation detail as you realize you're on the best path and want to converge on a solution. You finally arrive at a model which is suitable for implementation, suitable for automatic code generation from that model. You have the ability to review and to do static analysis at the model level, because that gives you the last candidate for what you're going to actually implement in software. The process of then generating the software is automatic code generation, just pushing a button based on the model, maybe setting some attributes of fixed point, floating point behavior, and other types of things, and generating the code, and then going through the normal compile, link, build process for the embedded software. But because of the verification and because of the need for quality assurance, you have the feedback loops as well, a lot of which, from a phrase standpoint, you're probably familiar with at DAC. Equivalence testing. How do you know that the binaries, that the source code match the design? What are the techniques suitable for doing that? Looking at the model, which represents the low-level design, how do you know that that represents the requirements, and how do you know that each requirement is adequately met by each aspect of the design? Very critical for aerospace, increasingly important for automotive, with standards such as the ISO 26262. And so how does this work in real life? I can show you a basic diagram, but it's better to show you a case study that shows it real. This is a situation with Scania Truck, based in Europe. What they wanted to do is to create an onboard driver assistance system that enables the driver and prompts the driver when to shift gears in order to maximize the fuel economy of the truck as they're going down the road. And that, again, is sort of emphasizes the primacy of the driver in these types of systems. And what they're doing is as a development process, they really rely on data. And what you see with model-based design is not just models, but you see a combination of models and data. Data used to create models, data used alongside models, and so on. A second aspect of the development method is the integration of that data and simulation information to be able to further the design process. Iteration, validating through road testing, fine-tuning and refining. It's very much of a circular and iterative process where you try and do as much as possible in the computer, but again, you need to leave yourself open to combining it with road tests and other types of information. In parallel, you're using the models for the other purpose, which is quality assurance. Creating testing frameworks, as they do at Scania, using test representations that are suitable for simulation, for emulation on processor, and for the test rig in the candidate vehicle or mule. And so the reuse of test cases, test definitions, and test vectors is critical in automotive. Another aspect of quality assurance is to be able to do the testing as much as possible in the simulation environment on your computer. You can do it much faster. You can explore scenarios that are either difficult or unsafe to try and do in a real-world scenario. And unless you very cheaply and inexpensively explore different environmental conditions that the vehicle needs to behave under without ever leaving your lab. And then finally, there's the application, the ability to constrain the designer to work with models of certain types, with certain guidelines. You can think of that as the equivalent of coding guidelines in VHDL or Verilog or in C code. How do you know you're working with a safe construct or safe subset of all the different things that you might want to explore? How do you refine your ideas to what actually you're going to consider doing, certifying, implementing, and maintaining? So this is the way Scania presents their view of the development process. I tried to situate them along the development workflow, and it's interesting to note that actually all the work happens, or starts to happen, certainly, before you get to the generated code. And there's really one key aspect of the primacy of the models in this type of an approach. A key aspect from our standpoint is that while automotive is a key industry for model-based design, it isn't the only industry that uses model-based design approaches. Here are some other examples. You have Renesys, who's developing image processing IP cores. FLIR, which is developing thermal imaging and developing them onto FPGAs. Isonia, which is developing mobile apps for asthma sufferers to try and understand and maintain and monitor their behavior. Think of it as a health app. In the medical area, you have Wyman, which creates life-saving transport ventilators, so that if someone is discovered at the scene of an accident and needs to be transported to a hospital, they can get whatever is needed in a triage form from the ventilator, which requires lots of different modes of operation. And in mobile communications, you have people like Docomo and Beijing Labs, who are looking at different ways, different scenarios for situating the towers, trying to understand the coverage, trying to understand the load of devices that can be sustained through different layout strategies. So over the years, MathWorks has worked with you guys, okay? This community to try and address the needs of automotive, aerospace, communications, and other areas as well. And this is just a partial list. I apologize if I'm going to offend anyone for not including you guys. But we do work with the major EDA vendors from the standpoint of integration with the HDL simulators for verification purposes, integration with the analog mixed signal modeling and simulation environments for characterizing system-level models of different types, and so on. We also work with people like ARM, STMicro, so that to make sure that the code that is generated using our code generation tools is optimized for the platforms that they need to be optimized for. And we also work with the FPGA vendors to make sure that the synthesis flow works as well to FPGAs as it does to C code, and as consistently as possible. And so the benefits of these types of collaborations that we're happy to have are these. Being able to do system design and verification where you're able to take implementation detail and bring it upstream if that becomes a constraint on the behavior of the system. Optimized code generation, as I mentioned earlier. Being able to target different types of devices, whether they're programmable devices, FPGAs, or ASICs. Trying to look at the trade studies between the different ways and the different characteristics of the different targets. and looking more at some of the things such as Zinc and Altera SoC have provided, which are hardware, software, co-design opportunities.
So let me bring it to a close and wrap up here. And you can see electronics and software are increasingly important pairing for us in the auto industry. You know, it's about certainly driving electronics costs down, leveraging Moore's Law, more functions, more features, more capability to create those kinds of experiences. Software is key, is important, and is getting more complex for us overall. And tools and processes are key as we apply these technologies to safety-related systems and so on, leveraging ISO 262 and other forms to assure these are safe and secure systems. Observations, I want to make a few observations and trends for you. It's not just the silicon that creates these experiences. Again, I told you I'd emphasize experience over and over again. Technology is an enabler. We're looking at end-to-end solutions from silicon all the way through to end-to-end application. Electronics continues to grow rapidly in the industry. Solutions will increasingly have our product design organizations working with our IT organizations as cloud-based interfaces and seamless integration with the cloud. It becomes important. And we'll continue to focus on experience. We expect the underlying technologies and stacks and so on to work flawlessly to create these great and high-value experiences for our customers. Some technologies that are going to be important to us looking out into the future, now and into the future: NFC, Wi-Fi, Bluetooth, LTE, advanced LTE, networking technologies to transfer all this information around in the vehicle. We can no longer rely on speeds and capability of the CAN network. Multi-core and virtualization and hypervisors for safety and security of these systems. Alternate forms of processing, DSPs, GPUs, et cetera, as well as CPUs. Advanced display technologies, heads-up, DLP technologies, laser projections. A big part of it is really HUD, heads-up display technology that keeps the driver's eyes focused on the road. Power management, increasingly important. An always connected vehicle needs to have some power. So how we manage these systems, not only within an individual ECU or function, but also across the entire vehicle is important. And then fast prototyping. How can we build these systems and test these systems very quickly to verify they'll deliver the experiences we want? Some trends looking forward: biometrics. You know, I talked about the need to personalize, make the vehicle adapt to you. But how do we know it's you? So biometrics is important. Car-to-car, car-to-infrastructure communication technologies, mesh networks, and so on. Seamless syncing across ecosystems, whether it's Google or Apple or Microsoft or Amazon or whatever. Customers have to have choice. We need to be agnostic to it. Rapid connect and disconnect and reconnect so that it's seamless to the customers. They can't tell when it's hopping between different connectivity. Real-time streaming analysis tools and big data. Tremendous amounts of data are created by the vehicle itself. Tremendous amounts of data exist in the network that can help create a better experience. How do we manage? How do we analyze? How do we create experiences with that? Advanced machine learning, patterns, personalization, habits, and so on. Again, there's so many things that should just work. Shouldn't have to ask the customer for. Validation and verification tools and processes, really important. Jim pointed out the opportunities we have using the tools that are being developed, that exist and are being developed. Sensor fusion and lower cost sensing methodologies. Human-machine user experiences, a lot of discussion around gesture and touch and heads-up displays and so on. Again, solving that to create a distraction-free experience. And of course, secure, private, and upgradable experiences as well. So my call to action for you to help us out in this community really begins with, again, focus on the experience. Technology is extremely important to create experiences, and how do we get from the technology to the experience seamlessly? Second, hardware and software technology are the enablers, but tools and processes are critical to us. We're not going to be able to manage these systems and the creation of these experiences using what we've done in the past. We have to change going forward. Complexity is going to continue to grow. A lot more interdependence of these systems, both on the vehicle and off the vehicle, and tools and methods can help deliver that. And the future certainly is really exciting for us. This is a great time to be in the auto industry. We have some great opportunities going forward. Hopefully we presented some that you hadn't seen before and spark your interest. But in the end, the customers will love their cars only if they can say it just works. So thank you very much for your time. We appreciate the opportunity to be here. It's a great place to talk about how these industries can get together to create great experiences for our customers. And I thank MathWorks and Jim for their support as well.
Thank you.